we're going to talk about electrochemistry in this chapter. And electrochemistry, as the name suggests, is basically looking at the intersection between electric current and chemical reactions. In fact, there are two processes or two types of processes that we'll be looking at under this topic, right? So, firstly, the first thing I want to point out here is the fact that electrochemical processes are redox reactions. Now, redox is something that you should have met before in Chem 1, and we're going to review some stuff that you should have covered in Chem 1, all right? But the important thing I want to bring to your attention is that there are two types of processes. One where there is energy released in the form of electric currents that is the result of a spontaneous reaction. Another type of electrochemical process is one where electrical energy is actually used to drive a non-spontaneous reactions. Now, the term spontaneous, let me just briefly state what that means, because this is something we're going to meet later on in the next chapter, which deals with thermodynamics. So basically, when we're talking about a spontaneous process or a spontaneous reaction, we're talking about a reaction that will occur by itself without any assistance whatsoever, all right? So if you, for example, mix together a solution of, let's say, silver nitrate and sodium chloride, you'll get the formation of a solid. That just happens without you doing anything extra or providing any energy for that particular reaction to take place, all right? So basically what we're talking about here in the case of the first type of process is where a reaction takes place by itself, and the energy produced by that reaction is going to be in the form of an electric current. And then the second type of process, which we're going to meet later on, is where we have to actually use some electrical energy source in order to cause a reaction that would be otherwise non-spontaneous. All right? Okay, so with that said, as I said before, we need to revise some terms that you would have met in General Chemistry 1 as it relates to redox reaction, all right? So we're going to start off from the simple and then move on to the more complex. So here we have a very simple example of a redox reaction, the reaction between magnesium and oxygen to form magnesium oxide. Now, just to remind you what redox or what reduction and oxidation is, let me just go to my writing function here. So basically, there are several definitions, by the way, of redox. The one that will be probably the best for the purposes of our discussion is that oxidation involves loss of electrons, all right? And reduction, whoops, sorry about that, reduction, do down here, reduction involves gain of electrons, right? And in my Chem 1 classes, I like to tell students or show them this mnemonic that they can use to remember what these terms mean. Oil rig, right? Oxidation involves loss of electrons, reduction involves gain of electrons, right? And there's another mnemonic which is used, which I can't recall right now. Anyway, so in this example of a redox reaction, we have magnesium undergoing a change from, sorry, let me go back to my pointer. Okay, so magnesium is undergoing a change where magnesium here, which is neutral, is converted to magnesium ion. So that is the half reaction shown here, right? The magnesium is converted to the magnesium ion and it loses electrons in the process. In the case of the oxygen on this side is converted to the oxide ion on this side, all right? And that is as a result of the oxygen gaining electrons to form the oxide ion, all right? Now, in order for this equation to be balanced, these would have to be the half equations that are associated, which when you add them together, you're going to end up with the net equation right here. So you'll notice that here we have electron loss by the magnesium, that's oxidation, and here we have electron gain by the oxygen, that's reduction, all right? And one key thing I want to remind you of that you should have learned in your Chem 1 course, is that in redox reactions, the number of electrons lost must be equal to the number of electrons gained, right? And that is a constant theme that you're going to see right throughout this discussion, not only here for this simple example, but even for the more complex examples, you're going to see that the number of electrons lost and gained must be the same in order for the redox reaction to occur. And not only occur, but when you add them up, you end up with the balanced entire equation. All right? Okay. Now this thing is, okay, so the next thing we're going to talk about here is what is called the oxidation number. In some textbooks, they call this the oxidation state, right? So the definition of the oxidation number, and this is specifically in regards to atoms of elements in either a molecule or an ion or even by itself, all right? It is the charge that the atom would have in a molecule or an ionic compound if the electrons are completely transferred. So that's the working definition of oxidation number. And there are some rules for you to determine the oxidation number of different elements in particular compounds. And being able to make predictions as to what the oxidation numbers are will help you in terms of determining whether or not a particular element is oxidized or reduced. Okay, so here's the first rule. And by the way, you don't need to memorize these rules. What you'll find is that when you solve problems or when you try to do problems and you're applying these rules, eventually you'll find yourself knowing these rules, all right? So I'm just going to go through these rules right here. The first of which is that free elements that are not combined with anything will have an oxidation number of 0, all right? So basically, any element by itself, not combined with anything, else except maybe this an identical atom of the same element, their oxidation numbers are 0. And these are just some examples right here. Even those polyatomic molecules like hydrogen and oxygen and phosphorus, where there are more than one atom per molecule, the oxidation number of each element in that molecule will be equal to 0. All right? The second rule says if you have a monatomic ion, the oxidation number is equal to the charge on the ion, right? So basically, whatever the charge is on the monatomic ion, that would be its oxidation number. And some examples are shown here, all right? So just to highlight one example, the iron 3 plus ion, the oxidation number is plus 3, all right? Or in the case of the oxide ion, the oxidation number is minus 2. Okay, the third rule says, and this one is specific for oxygen, right? This one says the oxidation number of oxygen is usually minus 2, but there are some exceptions. And the exceptions would be any compound that contain the peroxide ion and hydrogen peroxide, in which case the oxidation number is minus 1, right? So pretty much, if you're not dealing with peroxides or hydrogen peroxide, then you can simply assume that the oxidation number is minus 2. But in the case of peroxides and hydrogen peroxide, the oxidation number is minus 1. Okay, so that's rule number 3. Rule number 4. And this rule is specific for hydrogen. This rule says that the oxidation number of hydrogen is plus 1, but there are some exceptions again, and that those exceptions, will involve situations where the hydrogen atom is bonded to a metal. In those cases, the oxidation number is minus 1, all right? So for example, in the case of water, where hydrogen is bonded to an oxygen, so let me just give a couple of examples here. Where is that thing? Okay, so in water, the oxidation number of hydrogen is plus 1. But in, let's say, sodium hydride, where hydrogen is bonded to the sodium atom, the oxidation number of hydrogen is equal to minus 1, all right? So that's basically how that works, all right? Okay, the next rule, rule number 5, says that when you have a metal that is either in group 1A or group 2A, then basically when those metals are combined with other elements, their oxidation numbers will be equal to plus 1 or plus 2 respectively, right? So basically the group numbers would be the same as the charge on the, or the oxidation number of the metal if they're combined with other elements. So this sentence here is not actually complete. Let me just add a little note right here saying that when combined with other elements, right? That's very important. When combined with other elements, all right? So when these elements are combined with other elements in a compound or ion or molecule, the group numbers would be the same as a charge. And that's for group 1A and group 2A metal. Now, fluorine is very specific. The rule for fluorine is that its oxidation number is always -1, right? That is without exception. It doesn't matter what it's bonded to, only if it's bonded to itself, right? But if it's bonded to other elements, then the oxidation number of fluorine is -1 always, all right? Rule number 6, the sum of the oxidation numbers of all the atoms in a molecule or ion is equal to the charge on the molecule or ion, all right? And this rule is very useful because you can determine the oxidation number of elements that were not mentioned before based on this rule. And we're going to see an example of it right now. So here's an example. The question is asking here, what are the oxidation numbers of all the atoms in this particular ion, which is the bicarbonate ion, right? Now, based on the rules that we learned before, in the case of hydrogen, we know that the oxidation number of hydrogen is +1, and we know that the oxidation number of oxygen is -2 based on rule number 3. So the question now becomes, what's the oxidation number of carbon? Well, we can exploit rule number 6 in order to help us to determine that, because rule number 6 says that the sum of the oxidation numbers of all the atoms in a molecule is equal to the charge. So we know that the oxidation number of hydrogen plus 3 oxygens plus the carbon is equal to -1. So we can set up an equation which solve for the oxidation number of carbon. So 3 times -2, which takes into account the oxygens, right? There's a 3 here because we have a subscript of 3 here in the formula. And then we add that to the oxidation number of hydrogen, which is +1. And then we add that to the unknown, which is the oxidation number of carbon. And we add all of that up and equate it to -1. And then all we have to do is basically solve for the question mark right here. And you see that the result is that the oxidation number of carbon is +4, right? So that's basically how we can use that rule to help us to determine the oxidation number of carbon based on the rules concerning the oxidation numbers of hydrogen and oxygen. Okay, we're going to stop here for today. Oh, and then the next thing we're going to talk about is basically how do we balance redox equation, which should be a bit of a review for you guys, all right? Okay, until then.